How is Nesterov's accelerated gradient descent implemented in Tensorflow? The documentation for tf.train.momentum optimizer offers a use_Nesterov parameter to utilize Nesterov's accelerated gradient (nag) method. However, nag requires the gradient at a location other than that of the current variable to be calculated, and the apply_gradients interface only allows for the current gradient to be passed. So I don't quite understand how the nag algorithm could be implemented with this interface. The documentation says the following about the implementation. Use_Nesterov, if true use Nesterov momentum. See Sutskever et al., 2013. This implementation always computes gradients at the value of the variables passed to the optimizer. Using Nesterov momentum makes the variables track the values called theta_t plus mu v_t in the paper. Having read through the paper in the link, I'm a little unsure about whether this description answers my question or not. How can the nag algorithm be implemented when the interface doesn't require a gradient function to be provided?
TL, drive. TF's implementation of Nesterov is indeed an approximation of the original formula, valid for high values of momentum. Details. This is a great question. In the paper, the nag update is defined as where f is our cost function, theta t are parameters at time t, mu the momentum, lambda the learning rate, vt is the nag's internal accumulator. The main difference with standard momentum is the use of the gradient at theta t plus mu.vt, not at theta t. But as you said, TensorFlow only uses gradient at theta t. So what is the trick? Part of the trick is actually mentioned in the part of the documentation you cited. The algorithm is tracking theta t plus mu.vt, not theta t. The other part comes from an approximation valid for high value of momentum. Let's make a slight change of notation from the paper for the accumulator to stick with TensorFlow's definition. Let's define it equals vt, lambda. The update rules are changed slightly as the motivation for this change in TF is that now A is a pure gradient momentum, independent of the learning rate. This makes the update process robust to changes in lambda, a possibility common in practice but that the paper does not consider. If we note psi t equals theta t plus mu dot lambda dot at, then this last approximation holds for strong values of momentum, where mu is close to 1, so that mu minus 1 is close to 0, and f psi t is small compared to A. This last approximation is more debatable actually, and less valid for directions with frequent gradient switch. We now have an update that uses the gradient of the current position, and the rules are pretty simple, they are in fact those of standard momentum. However, we want theta t, not psi t. This is the reason why we subtract mu dot lambda dot at plus 1 to psi t plus 1 just before returning it, and to recover psi it is added again first thing at the next call.
I couldn't see any info on this online, and the linked paper certainly wasn't helpful, so I had a look at the unit tests for tf.train.momentum optimizer, from which I can see tests for the implementation of both classic momentum and nag modes. Summary. Where Occam starts at 0 and is updated at every step. The above is a modified version of the formulation in the unit test, and I find it a bit confusing. Here is the same set of equations arranged with my interpretation of what each of the parameters represent. I could be wrong though. In other words, it seems to me like TensorFlow's implementation attempts to guess the adjusted gradient in nag by assuming that the new gradient will be estimated by the current average gradient plus the product of momentum and the change in the average gradient. I'd love to see a proof for this. What follows is more detail on how the classic and Nesterov modes are implemented in TensorFlow as per the tests. Classic momentum mode. For use_Nesterov equals false, based on the .ts basic function, we have the following initial parameters. Actually, the above are just the first element of the grads_0 and vars_0 arrays, but I'll just focus on a single value. For the subsequent time steps, we have which I'm going to interpret as meaning. If we assume that for the purposes of the unit test grad underscore 0 equals grad underscore 1 equals grad, then this makes sense as a formulation of classic momentum. Nesterov's accelerated gradient, nag, mode. For use underscore Nesterov equals true, I had a look at the underscore update underscore Nesterov underscore momentum underscore numpy function, and the test Nesterov momentum test case. The underscore update underscore Nesterov underscore momentum underscore numpy function has the following definition. And it is called in the unit tests like this.
If you ask what channel, please consider subscribing.